Welcome to part 3 in the video series of simulating a supersonic rocket using Ansys Fluent. In this video, we'll take the cleaned and prepped geometry from parts 1 and 2 and mesh it using Fluent's Watertight meshing workflow. If you have previously saved CAD files and want to reopen them to start the meshing process, or mesh a CAD file that was provided to you, you can launch Fluent in the meshing mode as shown. In the Launcher dialog box, you must specify your working directory, the number of processors to use, double precision, the dimensions of your model, and the meshing mode is selected as well. Once the program launches, we'll open the Watertight geometry workflow to start the meshing process. Then, select the file to import from the file browser that opens, selecting the discovery file of the cleaned and prepped geometry. Once imported, the geometry object will appear in the viewport. The geometry is manipulated with the same mouse and keyboard controls as in Discovery. All bodies from the geometry file are shown, including the bodies of influence. By hiding the symmetry plane, the BOIs can be seen more clearly. Then, hiding the BOIs, the outline of the rocket geometry from the simulation becomes visible. The BOIs are used to create local sizing parameters to control the mesh size in certain regions. Here, we'll select the body of influence, the desired BOI region from the labels, and set the target mesh size. For the nose cone, 6 mm is used. The sizing control should be named with the appropriate zone it influences for ease of use. The remaining BOIs are created with target mesh size varied depending on their region. Local sizing helps to control the cell size in areas of the domain where abrupt changes in flow properties are expected. For this simulation, the refined areas will improve solution accuracy near shock waves and wake regions. Here we have used bodies of influence to control the volume mesh, but a similar effect can be done through surface sizing controls such as local face size and proximity. Next, we'll generate the surface mesh by assigning a minimum and maximum cell size for the rest of the domain. The red boxes in the display window show the approximate size of those cells. A growth rate of 1.2 and 2 cells per gap are used as the default values for the global mesh. Once the surface mesh is generated, the statistics are reported in the console. A max skewness of 0.7 is desired. This mesh is sufficient. However, if required, you can insert a task to improve the surface mesh just below generating the volume mesh. This will then reduce the max skewness value. Next, we'll describe the geometry with only one fluid region, and then update the boundary conditions. These can also be updated later in the simulation setup. To set up the boundary layer controls, we'll decrease the growth rate to 1.1 and increase the number of layers used in our boundary layer cells to 12. This is done as we know we're simulating a high-speed flow, and will give a good first estimation of the cell size needed for a good Y+ value. With all mesh controls in place, we can now generate the volume mesh. By attempting to change the maximum cell length, we can see that the program automatically computes the maximum cell length based on the surface controls provided. The time to generate the volume mesh depends on the CPU resources used, the local sizing, fidelity, and the total size of the final volume mesh. Once completed, the mesh statistics show a million mesh cell with 0.18 minimum orthogonal quality. This minimum is above the 0.15 suggested. With the clipping plane enabled, we can see the volume mesh that was generated, the different fidelity cell sizes from the BOIs and how they grow into each other and extrude out into the far field volume mesh, as well as the boundary layer cells that were created. Again, this boundary layer is a good first pass estimation. For accurate modeling of drag and shockwave boundary layer interactions, a Y+ value of approximately 1 is required. Using the flow properties, you can calculate the first cell height required for a Y+ of 1 and assign that to the first cell height of the boundary layer. Or, an initial simulation can be run with the current mesh, and the geometry can then be refined and remeshed using this initial simulation results. For improving solution fidelity and increasing the resolution of shockwaves depicted within the flow, we can also adapt The volume mesh. This volume mesh refinement is best done with Fluent's adaptive meshing controls once an initial simulation is complete. This is discussed later in the workflow. Once you're happy with the mesh generated, inspected it, and ensured the minimum quality is above 0.15, we're now ready to switch to the solution. Now in the solution workflow of Fluent, we can start setting up our simulation, which will be covered in the next video.